What if you could design your perfect child, changing their IQ, strength, even how long they'll live? Sounds like science fiction, right? But with CRISPR, it might be closer than you think. CRISPR, short for clustered regularly interspaced, short palindromic repeats might sound like a complicated mouthful, and it kind of is. But at its core, it's a tool that lets scientists edit DNA with unprecedented precision. To understand how revolutionary CRISPR is, imagine your body as a book written in a four-letter alphabet: A, T, G, and C, the bases of DNA. Every instruction about how your body works, from your eye color to how your cells fight off disease, is encoded in that sequence. Now imagine if we had a pair of super accurate scissors that could go in and cut out a typo in that book, or even replace it with a better sentence. That's essentially what CRISPR does. But where did it come from? Believe it or not, CRISPR was first discovered in bacteria, where it serves as a natural defense system. When viruses attack, bacteria save a snippet of the viral DNA inside their own genome, like a molecular mugshot. If the same virus comes back, the bacteria use a protein called Cas9 to cut it to pieces using that saved sequence as a guide. Scientists figured out that this system could be repurposed. By programming CRISPR-Cas9 with a custom RNA guide, they could tell it exactly where to cut inside any DNA sequence, including that of humans. And once the DNA is cut, the cell's natural repair process kicks in, either deleting the gene, fixing it, or even adding something new. This is what makes CRISPR revolutionary. It's cheap, fast, and incredibly precise. Unlike older gene editing methods like TALENs or zinc finger nucleases, CRISPR doesn't require building a whole new protein for every new target. You just change the guide RNA. It can be used in embryos, adult cells, or even in living organisms. In just a few years, CRISPR has gone from a discovery in microbiology to one of the most powerful tools in biotechnology. It's already being used in labs around the world, not just to study DNA, but to rewrite it. But as with any powerful tool, the question isn't just how it works. It's what we choose to do with it next. CRISPR is no longer just a theory written on whiteboards in university labs. It's being used in the real world right now, changing lives and challenging limits. 1. Treating genetic diseases. One of CRISPR's most promising applications is in the treatment of inherited genetic disorders. Conditions like sickle cell anemia, beta thalassemia, and hereditary blindness are caused by small mutations in our DNA, and CRISPR gives us a way to fix them at the source. In 2020, a historic moment occurred. The first patient was treated with a CRISPR-based therapy for a blood disorder. The results were astonishing. Patients who once required constant blood transfusions showed signs of long-term recovery. CRISPR isn't just masking symptoms, it's rewriting the genetic code itself. 2. Revolutionizing agriculture gene editing is also transforming how we grow our food. CRISPR has been used to engineer drought-resistant corn, disease-resistant bananas, and even non-browning mushrooms. Unlike older methods of genetically modifying crops, CRISPR doesn't require adding foreign DNA. This makes it a more natural, and often more publicly accepted, form of genetic modification. 3 cancer research and immunotherapy scientists are using CRISPR to reprogram immune cells to better recognize and destroy cancer cells. Early clinical trials involving edited T cells have shown potential in treating certain types of leukemia and lymphoma. By precisely modifying genes that control immune response, CRISPR is giving doctors new weapons in the fight against cancer. 4. Gene drives and vector control. In places where malaria kills thousands each year, CRISPR is being used to engineer mosquitoes that are incapable of spreading the disease. Through a technique called gene drive, these modifications are passed down rapidly, potentially collapsing entire disease-carrying populations. Of course, this raises environmental concerns. What happens if we accidentally disrupt an ecosystem? But the potential for saving lives is massive. From labs to farms to hospitals, CRISPR is already changing the world in ways that were unimaginable just a decade ago. But if that's what we can do today, what about tomorrow? Imagine walking into a clinic in the near future and choosing your child's eye color, height, intelligence level, or even how resistant they'll be to future diseases. Sounds like a scene from a sci-fi movie, but it's not as far off as you might think. This is the controversial realm of designer babies, and CRISPR is the technology that could make them a reality. What is a designer baby? A designer baby is a child whose genetic makeup has been artificially selected or modified, usually to eliminate certain genetic disorders, but potentially to enhance physical, cognitive, or even emotional traits. In theory, CRISPR could allow parents to eliminate the risk of inherited diseases like cystic fibrosis or Huntington's boost intelligence by targeting genes related to brain development, modify appearance traits like height, eye color, or skin tone, enhance athletic performance or resistance to fatigue. The real case? He Jiankui's experiment. In 2018, Chinese scientist He Jiankuai claimed he had edited the genes of twin girls, Lulu and Nana, to make them resistant to HIV by disabling the CCR5 gene, which the virus uses to enter cells. The announcement sent shockwaves through the scientific world. While preventing disease is a noble goal, He's experiment crossed a major ethical line. He edited embryos, implanted them, and brought those edited humans into the world. Something no one else had ever done. The backlash was immediate and intense. He was sentenced to prison in China for illegal medical practices. The global scientific community condemned the move as irresponsible and dangerous. Many questioned whether the girls would suffer unintended side effects in the future. But perhaps the most disturbing question was this. Now that it's been done, what's to stop it from happening again? Therapy or enhancement? There's a huge difference between using CRISPR to treat diseases and using it to enhance traits. But that line is blurry. If we can prevent a child from having a learning disability, should we also boost their memory? If we can prevent low muscle tone, should we also enhance strength? Where does medicine end and engineering begin? Genetic inequality? If only the wealthy can afford genetic enhancements, we could be creating a world where genetic privilege replaces natural talent or hard work. This raises serious concerns about inequality, discrimination, and what it even means to be normal. CRISPR gives us power unlike anything we've had before. But with that power comes a choice. Will we use it to heal or to control evolution itself? CRISPR offers us unprecedented power to edit the human genome. But with that power comes one of the biggest ethical challenges humanity has ever faced: consent and future generations. Unborn babies can't consent to changes made to their DNA. When we edit an embryo's genes, we make decisions that affect not just one individual, but potentially countless generations to come. What right do we have to make permanent changes on behalf of those who can't speak for themselves? Therapy versus enhancement. Treating genetic diseases is widely accepted as a noble goal. But where do we draw the line between curing illnesses and enhancing human traits? If we can prevent disabilities, can we also boost intelligence or physical abilities? The boundary between therapy and enhancement is blurry, and that uncertainty raises serious ethical questions. Societal impact and inequality. CRISPR technology might be expensive and only accessible to the wealthy. If genetic enhancements become a luxury, we risk creating a society divided by biology, a new kind of genetic class system where only the privileged can afford to improve their children's genes. Off-target effects and unintended consequences. While CRISPR is precise, it's not perfect. Editing the genome might cause unintended mutations elsewhere, possibly creating new health problems. The long-term consequences of gene editing remain unknown, and mistakes could have irreversible effects. Global regulation and governance. Different countries have very different rules for gene editing. Some ban germline editing entirely, while others allow it under strict regulation. This patchwork of laws raises concerns about genetic tourism, where people might travel to places with looser rules to get genetic modifications. These ethical dilemmas are inseparable from CRISPR's power. As we stand on the edge of a genetic revolution, we must ask ourselves, who decides the future of humanity's DNA? The future of CRISPR is as exciting as it is uncertain. As scientists push the boundaries, we face incredible possibilities, eradicating hereditary diseases. Imagine a world where diseases like cystic fibrosis or Huntington's no longer exist because we can edit those faulty genes out of the human population entirely. Personalized medicine. Treatments tailored specifically to your unique genetic makeup could become the norm, making healthcare more effective and less invasive. Designer organs. Growing custom organs for transplant, potentially eliminating waiting lists and rejection risks. But with such power comes serious risks. Bioweapons. Could CRISPR be used to engineer viruses or bacteria designed to target specific populations? Unintended genetic consequences. Editing one gene might have cascading effects we don't yet understand, possibly harming ecosystems or human health. Social division. If only some can afford gene enhancements, societal gaps could widen dramatically. In short, CRISPR could usher in a golden age of medicine, or open Pandora's box. The choices we make now will shape human evolution for generations. CRISPR forces us to ask deep questions. What does it mean to be human when we can rewrite our own DNA? Are we gods guiding our own evolution, or recklessly meddling with forces beyond our comprehension? How do we define normal or perfect in a world of customizable genetics? Who gets to decide which traits are desirable? Some argue that gene editing is simply the next step in human evolution, a natural progression using our intelligence. Others warn of hubris, of unintended harm, and the loss of genetic diversity that nature has refined over millions of years. Whatever your view, one thing is clear. CRISPR doesn't just change genes, but it changes our relationship with life itself. It challenges our ethics, our philosophy, and our future. CRISPR technology is a revolution at the genetic level. It offers hope, power, and profound dilemmas. The question is no longer if we can redesign humans. It's whether we are ready for the responsibility that comes with that power. You made it all the way here. Brain spinning, questioning if time is even real. And you're still not subscribed? Look, this channel isn't just content. It's a mental roller coaster through black holes, brain glitches, and bizarre theories your school never dared to teach. If you're into stuff that blows your mind and makes you say, wait, Lasti, what did I just watch? Then yeah, you belong here. Smash that subscribe button so we can decode the universe together. Or at least get really confused trying. And hit the bell too, because if time is fake, notifications better be real. Let's get lost in the weirdest questions of existence. One rabbit hole at a time.